In the early 20th century, our understanding of gravity underwent a revolution. Isaac Newton's law of universal gravitation had dominated physics for over 2 centuries, describing gravity as a force acting at a distance between two masses. While Newton's equations worked remarkably well for most everyday phenomena, they faltered under extreme conditions, such as near massive stars or at the edges of our expanding universe. Enter Albert Einstein's theory of general relativity, a radical reimagining of gravity itself. At its core, general relativity proposes that gravity is not merely a force but a manifestation of the curvature of spacetime. Imagine spacetime as a flexible fabric, stretching infinitely in all directions. When an object with mass or energy resides on this fabric, it warps and bends the surrounding spacetime, much like a heavy bowling ball placed on a trampoline. Other objects moving nearby follow the curves created by this deformation, not because an invisible force pulls them, but because the geometry of spacetime dictates their paths. This elegant concept reframes gravity as geometry itself. Einstein's field equations, the mathematical backbone of general relativity, describe precisely how matter and energy influence spacetime curvature. These equations predict phenomena that were once unimaginable: the bending of light by massive objects, the gradual orbit shifts of planets, the stretching of time near black holes, and even the ripples in spacetime we now detect as gravitational waves. Each prediction, initially tested decades after Einstein's proposal, has been confirmed with astonishing precision, cementing general relativity as one of the pillars of modern physics. Perhaps most captivating is how general relativity connects the microscopic and cosmic scales. Time, often thought of as absolute, becomes malleable, flowing differently depending on the strength of a gravitational field. Space, once considered a rigid stage where events unfold, becomes a dynamic entity intertwined with time itself. Together, space and time form a four-dimensional tapestry whose geometry shapes the motion of stars, planets, and light across the cosmos. Beyond its theoretical elegance, general relativity has practical applications that touch our daily lives. The GPS, for instance, relies on precise timing signals from satellites. Without accounting for the slight but significant warping of spacetime caused by Earth's gravity, GPS readings would drift by several kilometers each day. In this sense, Einstein's theory isn't just a cosmic abstraction, it's a critical tool that guides navigation in our modern world. In the grandest sense, general relativity invites us to see the universe differently. No longer a static stage, the cosmos emerges as a dynamic, ever-changing landscape shaped by matter, energy, and the curvature of spacetime. From the gentle orbit of planets to the violent collisions of black holes, the universe dances to the geometric rhythms Einstein revealed. A dance that continues to inspire wonder and drive discovery more than a century after its conception.